Chapter 3, Part 2, Still Considering Energy. So the last part of the consideration of energy directly is the conservation law of energy. So the law of conservation of energy states the following. Energy cannot be created or destroyed, although it can be changed from one form to another. Now, moving away from energy, but we will return in a moment. Let's talk about another physical quantity that is also so important, and that is linear momentum. What is the definition of it, and how do we relate it in physical situations? Newton's first law states that objects in motion remain in motion unless acted upon by a force. Now, linear momentum is a measure of that tendency, the tendency of an object to remain in motion unless it's acted upon by an external force. Consider the following. The left, we have a depiction of a baseball at the top, baseball at the bottom, same mass. I'm sorry, the masses are the same in this case, although we call this one M1 and call that one M2. But M1 is moving faster, has a higher velocity, which means it has a speed in a given direction. In the bottom case, it has a lower velocity going in the same direction. So in the first case, the top case, the ball has a higher momentum than it does in the lower case. Consider this situation on this side. Now, M1 has a mass greater than M2. It is an iron shot. They're both now going to move at the same speed. V1 is going to be equal to V2 in this case, but still the momentum is higher in the top versus the bottom. So the mathematical equation then we get is that momentum then multiplies two quantities. Linear momentum is a product of an object's mass and its velocity, and it is a vector quantity. And so the magnitude of linear momentum is m times v. Okay, very good. Now, in the absence of outside forces, the total momentum, linear and angular, we'll come to angular momentum later, of a set of objects remain the same no matter how the object interacts with one another in the absence of force. So if there's no external forces acting on the object, the momentum is conserved as well. So this, like we had the conservation of energy, now there's this notion of conservation of momentum. So here is an illustration of that. A 40-kilogram girl running at 30 meters per second jumps onto a 10-kilogram sled that is initially at rest. So the sled is not moving initially. The girl is moving though. Now the question becomes, how fast will she and the sled move together after she jumps onto it? In a case where there's no external forces acting, say if she and the sled is on a slick surface. Here's the mathematics for that. The total momentum in each case must equal to the momentum in the latter case. So she has M1 times V1. That's the momentum that she has initially. And then when she jumps onto the sled, the sum of the two masses represented here by grouping M1 and M2 together times V2, becomes the momentum in the final case. This is a picture of that. So if we want to know then some specific quantity, we then can solve this equation. If everything else is known, we can find what we're looking for. So here's a case then. We want to know the speed in the final situation. M1 is known, V1 is known, and M2 is also known. You plug in the math here, you add the two masses there, that's 50 kilograms. That's 40 times 3 divided by 50 becomes 2.4 meters per second. That's the way you would do that problem. Here's the second one where momentum is conserved. A 100 kilogram astronaut accidentally throws away a zero point 0.5 kilogram camera during a spacewalk. If the camera moves off at 6 meters per second, how fast will the astronaut be moving? So you have to visualize the problem. The astronaut has a very large mass, 100 kilograms. The camera only weighs a half of a kilogram. The camera is thrown at a fairly high speed, 6 meters per second. Now, what's going to be the speed of the astronaut? Here's the mathematics. Momentum before equals momentum after. There's nothing moving until the astronaut throws the camera. So it's zero on the left-hand side because if there's no speed, although there's mass, there's no momentum. In the latter case, though, when the astronaut now has thrown the camera, the astronaut mass is, we call it ma. The velocity of the astronaut v sub a, although we don't know it at the moment, plus the mass of the camera times the velocity of the camera. This sum on the right must add to zero. So there must be a negative sign somewhere. That's the only way you can get two apparently positive quantities to add to zero. So now, since we want to know v sub a, we transpose the product of ma to the left-hand side of the equation and then solve for v sub a. Notice we get this negative sign in front of the mc times vc. We solve this, we get a negative 0.03 meters per second. This is quite interesting. The camera goes off at one speed, a positive 6 meters per second at one velocity, and the astronaut moves in the opposite direction at a negative 0.03 meters per second, based on the conservation law of momentum. This shows that situation. A rocket operates on the conservation of linear momentum. This now an astronaut is leaving the launch pad and hot gases are being ejected at a very high rate from the end of the nozzle of the rocket, and the rocket and the astronauts travel in this opposite direction. Hot gas is moving in one direction, and the rocket and the astronauts and whatever else is on the rocket travels in the opposite direction. Based on the conservation of linear momentum, uh, and the material expelled from the rocket engine is small relative to the mass of the rocket, but it's traveling so much faster, just as it was in the case with the camera being thrown and the astronaut being moving in the opposite direction. So here's an illustration of that. And by building multi-stage rockets, engineers can achieve higher final speed. The emptied engines, structure, and tanks are cast off. The remaining vehicle needed to burn less fuel to accelerate to a higher speed. This is an illustration of that situation. There is this other quantity we call angular momentum. which also we will find is conserved if there is no net torque acting on the object. So the angular momentum depends on mass, shape, and the rate of rotation. The angular momentum is conserved in the absence, as I said, outside torque. This is an illustration of torque lifting a barbell in this manner with the arms, and of course the muscles are needed to lift that. This is an illustration of a skater, ice skater, on a frictionless surface, and here the person is spinning slowly in this situation, rotating here in a counterclockwise manner. But as soon as the person raises up, stands up, and pulls the legs in together, the speed gets much higher, okay? Faster speed due to the conservation of angular momentum. I want to talk just a little bit about relativity. Einstein did some very outstanding work in the early 1900s, and he came up with the special theory of relativity uh, and the general theory of relativity as well. And in that, the frame of reference, when something is moving its position relative to something else, is called the frame of reference. That's how we can tell that something is moving. The laws of physics are the same in all frames of reference, moving at constant velocity with respect to one another. So if you're moving in your car at a constant velocity, or standing on the side of the road, all of the behavioral physics of a third something would appear the same to each of the two objects. Laws of physics are the same. The speed of light has the same value for all observers, though, and all other electromagnetic radiation traveling in free space have the same speed. It is 2.910 to the 8 meters per second squared, 186,000 miles per second. That's very fast. And lastly, there's some interesting situations that occur based on the theory of relativity. It is that time is not absolute, length is also not absolute, nor is mass. An observer moving with constant speed v measures his craft to have a value of L sub 0. He or she is moving with the craft, and measure it to have a mass of M sub 0. And in a time, make that measurement in a time of T sub 0. Person stationary measures something different. A person measures the length as being shorter than L0. He measured time as being longer than T sub 0 and measure mass that's being greater than T sub 0. I won't give the mathematics for this expression. Finally, though, out of Einstein's theory of relativity has emerged this very famous equation, E equals to mc squared. The interpretation of this equation is that if you have energy E0, and if that energy can be converted, which it can, completely to mass, then the conversion is given by this equation. So rest energy, which is E sub 0 is what this is called, is equal to mass times the velocity squared. And this is a calculation of this expression here. And you see m equals E0 with c squared. When something has this amount of energy, it comes out to a very small amount of mass being uh, uh, release. Also, but out of the theory of relativity is that mass will deflect light. And this is represented here with an illustration. That if you have a you are observing a star, if you're long ways from the sun, this is the where the star appears to be. But if you are close to the sun, the star is going to appear at this point, but it's actually at that point. That's bring me to the end of this presentation.